Okay, we got good? Okay. All right, well, we got through probably the biggest, most painful stuff is really that first chapter. It's very powerful that you can do a lot of problems that would be really difficult, and maybe you need a computer to do it, but if you can kind of follow the reasoning that we use, you could see maybe how we could break any problem down using these methods. It's a mess. When there's a high degree of symmetry, there's Gauss's law, your friend, that can help you see through all the confusion. Hopefully, let's see if we can get on with this. Okay, it started with really the idea of, at least in the way conceptually, the idea of Michael Faraday. He was. We're going to come into a lot of the work he did back in the 19th century. He was a great experimental physicist. He didn't have a lot of formal training, particularly in math, and so he had kind of difficulty with that. So if you're in the same boat, you might just like this guy. He had a great, powerful way of visualizing things in replacing this. And this is the idea for a point charge, you have this inverse square law. And he's trying to visualize that. He says, well, I can picture that as these field lines coming out from this charge. And then where they are close together, the electric field's strong. Where they're spaced out more, the electric field's weaker. These charges would have to start on the charge, and they would go all the way out to infinity. That is a lone charge by itself. If there were negative charges, they'd come in from infinity. And so these are Faraday's electric field lines. And they're, again, a great way of visualizing that runs a little different from the way we usually think of vector fields. Usually you would think of a little vector field as a little vector here that would be maybe pointing away, and it would have a greater magnitude the closer it is and weaker as it gets out. That's all valid too, but these field lines are again a great way to visualize this, and they help tremendously in seeing behind Gauss's law. Now the idea that they're really pictured as these field lines, that they start on the charge, they go out to infinity. And now the idea of there's a number of things that follow the inverse square law. We've had gravity, we've got the electric field, also light, which you're going to show is very closely associated with electromagnetism. But if you picture this as something like a star, this is a good kind of mental image, and it's shining the light, that light is going to maybe pass through some window or some patch here. Maybe I've got a white square here and I'm illuminating it. It's got a certain amount of brightness. And then if I take that away and go out here twice as far, that light spreads in both the x and y direction. It's going to spread out over 4 times the area. So the light is going to create a kind of a pattern here that's 1/4 as bright as that, hence the inverse square law. And so this is, again, a great way to kind of visualize this. Now the idea of the electric field flux, as we're going to call it, are these electric field lines. And it is considered that this electric flux is the number of these electric field lines that pass through some area or surface. And that this flux is going to be directly proportional to the charge. The idea, if I go back slide, this idea, if I double the charge, I'm going to double the number of lines that I have here. Cut it in half, I'll have half this number. So anyway, this, and also, again, the electric field will be proportional to the area density of the field lines. So how strong they are. When they're very close together, the electric field is stronger than when they're all spaced out. So this forms the real fundamental basis of Gauss's law. Now this idea of flux, we could say, let's start with the idea of just a uniform electric field passing through some surface. This is a rectangular surface, width w, height h. And the idea that the E is the area density of the electric field lines, where they're close together. So think of that density, area density times an area is going to tell you the number of these field lines. and the number of these field lines is proportional to the charge. Now, this area density, the density of these are really where these field lines hit at right angles to the surface. And we want to be able to deal with more general cases. So if I take something like this larger rectangular region, I'm just kind of folding it back. This is similar to like a homework problem that you had, where it's a bigger area. It's still rectangular, but I dip it back in such a way that whatever field lines pass through this one will also pass through this lower surface. And so it has the same flux. Flux is the number of lines. Whatever number I had here, I've got the same number here. Kind of just to help with the geometry, I'm drawing this kind of a straight-on side view of this thing. Got the electric field coming in. I've got what we call the area vector is how we're going to formalize this. It's perpendicular to the surface. Right now it would be perfectly natural to say, well, is it pointing that way or is it pointing that way? Right now it's kind of arbitrary. I just let it point this way for now. Then I'm going to take and fold this area back. It's got a larger area, and its surface, the vector we have, the area vector, points normal to the surface, and its magnitude is the area of that surface. So that surface is going to be, I call this H prime and W. But you'll notice that the flux should be the same. The flux should be the E times that original area, call it A naught, that area where it's hitting at 90 degrees. Life is simple. Then that area is W times H. If I tip this thing back, this thing gets longer this way to catch these same charges, call that H prime. And there's a relationship between H prime and H. H prime times the cosine of theta is H. And so we can put that together. And we still get the same relationship that the flux is going to be E times the area. But if it's other than 90 degrees, we can kick in the cosine of theta. We'll make up for that difference, that angled surface that the electric field's going through. So in general, we'll write this, you might recognize this, and go along with this is the idea we'll formalize it as the dot product. That the electric field, the flux, the number of lines is the density of those dotted with the area vector that we're going through. Okay, in general, what we deal with when we get into Gauss's law is we're going to be dealing with closed surfaces. So this ambiguity of which way does the area vector point, we're going to go with the formalism that when we're on a closed surface, the area vector for all these little patches are all going to be perpendicular to the surface, and they're all pointing out. Okay, so if we look at the flux, let's say, through a small one here, we've got this way. The area vector is pointing out that way. The electric field's coming in, and I'm not going to do that. And any of these various patches show how we would basically take this property and we do this dot product of the electric field and these little points to get the flux through this surface. Again, the area vectors are pointing out here. They're also pointing out here. You will see when the electric flux or the field lines are going out of the surface, we call that a positive flux. Which is going to lead to a positive sign with our convention. And if we have the area vectors pointing out here while the flux comes in, that's going to be a negative flux. So whether it's a plus flux or a minus flux depends on those directions. Again, this stuff very visual if you can kind of get a feel for it. Let's go back to a real simple example. Let's say we place charge here, just a single ordinary charge, and put it at the center of a sphere. Now, this is just a mathematical shape, a Gaussian sphere. And the idea that on that sphere we could get the flux for this thing. And the way I've got it centered on the sphere. So things are nice and symmetrical. As we go around this sphere, radius r, we see that the electric field here is going to be the same everywhere. It's got the same density. I do expect from the symmetry that it's going to be pointing away from that charge. So that seems to make some sense. When we deal with the the idea of the net flux, we're going to want to get the flux through the whole surface, and we're dealing with closed surfaces. That's why this little circle, this symbolically represents a closed surface, and we take the electric field dotted with the area. Now the electric field is going to be right at the surface of that sphere. When we integrate that E, that flux, should be proportional to the charge I have inside. And to get that flux, we integrate E dot dA over all of those little surfaces. Think back to this kind of picture where you're going to break the thing up and you've got a bunch of little pieces. Each of these are a little dA, and the flux through it is going to be expressed as just E dot dA, and we would integrate that over the whole surface. Now, this flux should be proportional to the charge that's inside. Now, that proportionality constant is just some constant, and we're just going to make it up and say it's 1 over epsilon naught. Now, you might say, well, why didn't you just put it as epsilon naught? I'm not real sure. Other than a lot of the stuff we'll write later, it helps to put it in that form so it comes up on top. Yeah?
Sorry, I'm skipping to the bottom, but that last line, E naught equals K equals 4 pi, isn't that wrong? Would it be E naught equals 1 over 4 pi K?
Oh, somebody told me about that too. Yeah, yes. Thank you for catching. Let me get to that. And is there another one besides that?
Mine was actually a question on the previous slide about the EN. En would be the component along the normal. Oh. That's what they're referring to. I'll do some similar things later, but. But in the first picture, or the one that's labeled number 3, it's going in the opposite direction of the normal. So it would be either going the same way or the opposite.
Well, yeah, the normal would be pointing out from the surface, doing that. Here, the electric field's coming in. Right. So there is a component in this way, but you'll notice that it's in the negative direction. So we're going to get a negative here, whereas over here we'd get a positive. Okay? Yeah, good questions. Okay, and we're going to, in effect, do that here. Thanks for catching this. The idea of doing this integral, we can simplify this thing, this dot product, because the surface normal is all pointing radially outward. It's in the same direction as E, so that's a simpler version. And this is often going to happen, so the idea, we're going to go from the general case, Gauss's law, or Gaussian surface, to the specific case. In this case, we can get rid of the dot product. E should be the same magnitude all the way around that sphere, so I can factor that out. And then we integrate all our little dAs, and rather than actually go through that process mathematically, I already know the area of a circle is pi r squared. This kind of simplification is going to be real common in the types of problems we use, where this side is going to be relatively simple and trivial, and then on the other side we're going to say that that's going to be directly proportional. Again, that proportionality is 1 over epsilon naught, should be over here. So we can then solve for E and divide through by r squared. Now, I haven't screwed up here yet. I've got 1 over 4 pi epsilon naught r squared in a q here. But just reminding you that what we had been doing in chapter 23, we'd say, oh, point charge, we know that that's keq over r squared. So we have the two of them. Well, they should be expressing the same thing. So I can set the two things equal and put a big mental red X through this, because I did one of my usual moves here. I got to screw up something. you can solve for epsilon naught or Ke. Very often in the types of problems we're going to be doing, you'll probably want to take Ke and replace it with 1 over 4 pi epsilon naught. The book sometimes replaces epsilon naught. That would come up here, and so it would be 1 over 4 pi Ke. So anyway, check my math here. You'll see right away that this is definitely wrong. So scratch that one. Okay, Neon, thank you for catching and remarking on that. Okay, okay, now what happens if we move the charge off center of the sphere? Okay, now what is the flux? Is the flux going to be the same? Yeah, flux is the number of lines. Whatever I have number coming out of here, whether it's on the center or anywhere inside, the number of lines that are passing out here have to be the same. And so we're going to use that great simplification for this. If I happen to have the charge outside the sphere, what about the net flux?
0.
0, yeah, it's going to enter and it's going to leave. It doesn't matter, it doesn't have to, it could be any kind of shape, it doesn't have to be spherical, just kind of an arbitrary shape. They'll come in where the surface normal is at right angles to there, and then these field lines come in. So this is a negative flux, and this is a positive flux. Well, how many lines leave the surface? Isn't that equal to the same number of lines that enter the surface? And so the net flux for any charge on the outside is 0. Okay, so hopefully you can see this. Now the thing is, we can, I was just using some examples with single charges. We could have any number of charges. We could say the flux total, this really is the total flux, is going to be the sum of all the individual fluxes of all the individual particles. Let's say I've got 1 to n of them. I'm just going to add them up. Okay, and each individual flux should just be the Q over epsilon naught. And then this flux could be expressed with Gauss's law. Maybe I should have put a nice bracket around this. And then we just sum these up. So basically we do this kind of game for each charge. It should add up, when we add up all the charges, should be just the net charge. And the way we'll express that net charge is we'll say Q, everything inside is contributing to this. That's Q inside. On the outside, now I'm going to do a little move here that's mathematically, hopefully you can accept this. The idea that whether we sum things through an integral or do a direct summation, they're both the additive quantities. And we can sum things in any order. So we could also turn this around and we could do the sum first and then we could integrate. The idea that we would pick out some little patch of surface and we would look at the flux due to all the charges present, add them up, and then we would integrate that over the whole surface, a whole bunch of dAs, repeating that. The sum of this, since dA, we would be picking out a given dA, it would be the same. We can factor this out. This is a bit, I realize this is a bit abstract, but if you can hang on here. This sum of the electric field is the net electric field, the sum of all the electric fields due to all the particles. And so we can put that here. And this really forms what we call Gauss's law. Very powerful. It's totally true in general. Usually in general, though, that this integral is really nasty. The only time we're going to do Gauss's law is when this is simple, when it's trivial. And that happens in cases of high degrees of symmetry. Now, I realize my argument here is a little abstract, more than a little here, but the basic idea here could be exemplified with a little dipole. In fact, this is one of the practice problems. What's the flux sphere surrounding the dipole? Well, the idea, should be pretty simple. We can look at these as individual charges, this with a positive flux and the negative with a negative flux. And then it's kind of pretty obvious. But we can also say that, wait a minute, these electric fields lead to a net electric field. From the two charges, we do the vector sums. We'd have to do this at all points in space to get the electric field. So the actual net electric field looks like this. So if we look at this net electric field that looks, wow, very different than that, the idea is that it should be the same whether I keep these charges separate and add up the net charge is 0 and the net flux is 0, or whether I actually do this integral, which looks like it would be extremely nasty with different r's and different angles, different electric fields, but I can make one startling conclusion that, hey, this has got to be the same as that. And that's the net charge is 0 and the net flux is 0, even though I can't tell just by looking at that. So that was kind of my argument. You could have any number of these, deal with them as individual charges, but it also applies to the net electric field. And that point is important to realize, that when we do Gauss's law, we're dealing with the net electric field here. And it's going to be dependent on the charges that are total charge that's inside. Both plus and minus, they add up. Pluses are plus and minuses are minus. They might add up to 0. Okay, so hopefully you get a little bit of that. Let's put this to use here. Something with a high degree of symmetry. Now, rather than a point charge, let's do a charged sphere. Insulating material has uniform charge density ρ and a total charge q. Derive, okay, show your work, expressions for the electric field in both the interior and exterior regions of the sphere in terms of the total charge and the distance from the center of the sphere. Okay, so here is a kind of crude picture here, but this represents my sphere here. This is the charged sphere. I'm going to first do it on the outside, that is r greater than a. So again, a is my radius of my charged sphere. R represents the variable out to some point in space. So let's say I'm at this point. I want to get what the electric field is at that point. R is my variable that points out to that point, and I'm going to take advantage of that. Excuse me. Okay, so if I'm outside the charged sphere, where R is greater than A, we can write Gauss's law. It's totally true, general all the time. In this case, we've got spherical symmetry, so that E and dA, the dot product with them, the cosine of 0 degrees, since the normal vector and E are going to be in the same direction, that's going to just go to 0. We're going to have, and E, because I'm this Gaussian sphere, I'm getting a little ahead of myself, I chose this surface. It's a mathematical imaginary sphere. I'm choosing it because it has these symmetric properties. The idea that E is the same everywhere around there, at least the magnitude, of course it's pointing off radially outward, but the magnitude is the same, and I've gotten rid of the vectors here with the dot product. I can factor that out, and then I integrate my dAs, and this part of it is the same as it was on the previous simple problem. It's E times 4 pi r squared. This is the area of the sphere. This sphere is not the area of the charged sphere, but it is R. It is the area of my Gaussian sphere. And that's equal to the total charge that's inside, which he tells us is Q over epsilon naught. And then we can go ahead and get that E dividing through. You'll notice that this is of the same form as that of a point charge. So when we're actually sitting on this region outside the sphere, the electric field is coming out, and from what we would see if you were sitting there as far as the electric field, it would be the same as if I took this whole charge and crunched it down and made it a point charge at the center. The electric field on the outside would look that way. However, the electric field on the inside doesn't look that way. We're going to go inside. Here's where I'm going to change my R. So again, we just did this on the outside where R is greater than A, sitting out here. That was our Gaussian sphere. On this one, the Gaussian sphere, we're going to embed inside here. Suppose inside the sphere I want to get what the electric field is. Well, I want to set up a Gaussian surface, and I want to use that spherical symmetry, so I'm going to put that in there. That's going to be my Gaussian sphere. Let me go to the next page here and go to details inside the charged sphere, where R is less than A. Here, my picture, this is A, so this red thing represents the whole charged sphere, the solid. And if I want to get at the electric field that's inside there, R is my variable. It points from the center to that Gaussian sphere. I'm embedding that spherical Gaussian surface in here. And I want to get at what the electric field is at the surface of the Gaussian sphere. So again, I set it up. Gauss's law is always true. These steps, E and dA, are very often working together. We end up with, they're in the same direction, so the dot product, it becomes a scalar. E comes outside, and then we integrate our dAs. Well, that's just going to be, it's a spherical surface, 4 pi r squared. And that's equal to the charge enclosed. And that charge enclosed is, let's come over here for a second. Let me come back to here. Q enclosed. Now he notices he has charge sphere, has a uniform charge density rho and a total charge Q. He wants us to derive expressions for the electric field in both the interior and exterior regions in terms of the total charge and distance from the center of the sphere. Okay, a little note on charge here. This idea of, again, charge density. What is that? We can look at the total charge inside is going to be the charge density, whatever that is, times the volume of the sphere. Now, the volume of the sphere, what I'm doing is going inside. Remember, I need the Q that's inside this sphere. This stuff on the outside, I will not be counting. This is outside the sphere. All of the points here have a flux where they're going in and coming back out. They wipe out. All I care about is the charge that's inside. But getting at that would be the density times the volume, 4/3 pi r cubed, for that of the sphere. The total Q would be along the same lines, except I would go from just a generic R all the way out to A, and that would represent the total volume. So the total volume times rho is that. Or if you want to solve for rho, we can put it in this form. And we've got rho is some function here of Q. In fact, I can make use of these relationships. Let's come back over here. So again, Gauss's law, the left side is pretty simple. Q enclosed is where it gets a little more challenging. Q enclosed is going to be this. It's going to be the density times the volume. Well, volume of what sphere? The Gaussian sphere, not the whole charge sphere, just the stuff that's going to be inside the Gaussian surface. Solving for E, you can see that, wow, this is some things are going to cancel. The 4 pi's are going to go out. You're going to end up with the density over 3 epsilon naught is going to be R times R. Something that's curious here, that the electric field is going to be proportional to R. So that means that if we're going to plot, let's say, the strength of the electric field versus R, it's going to be proportional to R. It's going to start when R is equal to 0. It will be 0, and it will go all the way up to the side, right to the edge of the solid sphere. Then once we go outside, we've already looked at that being acting like a point charge, so it's going to fall off with the inverse square. It's going to be something like that. Now, he asked for it to express it in terms of total charge Q. So what we can do is substitute, well, back in for rho, what it was for the whole charge sphere. Anyway, you can do the math and see that it comes out with this same relationship. Big thing that you want to see, it is proportional to the radius. Okay, so there's not too many things he can do to you. Yeah.
So when you were replacing Q in, you used the rho with the 4/3 pi r cubed. But then when you were replacing the rho later, you were using it for the 4/3 pi a cubed. Is that because rho's uniform? Or?
Right. Yes. Okay. Yeah, big important point here that it is a uniform positive charge density.
So it wouldn't work if rho is not uniform?
Right. In fact, I want to get to just that issue because that's more typical of what he might do.
If we expand rho, isn't it the same that Q inside is equal to the ratio of the Gaussian surface over the volume of the Gaussian surface over the volume of the charged sphere times?
Yeah, you can do that as long as, what he's saying is kind of like do like a proportion. And we can do the problem that way, can say, hey, the whole charge is Q compared to A, or I should say compared to A cubed. Boy, we want to deal with some...
If you make rho Q over V, then you just swap the Q and the 4/3 pi over H to the third, and then you have the volume of the Gaussian surface over the volume of the total thing times Q total, and that would be the Q inside.
Right, yeah, so you can, do it as kind of a proportion. And that's how I was doing a lot of the problems earlier, where I kind of set them up as a proportion. And that will certainly work. Now, one reason I'm kind of starting to steer clear of that is precisely because likely there's not too many things he can do. Gauss's law, you've got really three types of problems. You got spherical symmetry, you got cylindrical symmetry, and you've got planar symmetry. What happens, let me now give you a hypothetical one. What if there's a variable charge density? Anticipating your problem. And now here he could just make something up. And he might just make something up that makes the calculus easier. Suppose the sphere has a non-uniform charge density. And that's rho is, let's just make up this function that's some constant alpha times r squared. Now, what we need to do is we need to get some charges, and here's where it's really advantageous to use the charge density method rather than just do some proportions. In fact, we'd run into trouble if we just do proportions. The first off is we might need to get the total charge on this thing, particularly if we want to get the electric field out here anywhere on the outside. I just need Q enclosed, and that just represents the charge of that sphere, the whole charge. And so if he gives me in terms of charge density, I need to figure that out first. And so I can get the total charge. Now this is where it gets to be a little tricky. The idea is that we want to get the whole charge of the sphere. So we're going to break it up into a bunch of layers. Think of like layers of an onion that are going to be stacked up. And that's this kind of pinkish or purplish ring here. I've got it drawn as a ring. Keep in mind this is actually a sphere. And so we're going to get the charge inside that ring. That ring would be the charge density, this alpha r squared. When I'm using r sub q, so not confuse it with these other r's, this would be the r of that particular ring or that layer of material. And so it would be the density would depend on that. It's proportional to the r squared, so it's alpha r sub q squared. And then we take it times the volume of that layer. That layer again, like a layer of an onion. And this is 4 pi r sub q squared. This is the area of that sphere times its little thickness, dr. So that's actually a volume. But it is, I'm not saying 4/3 pi, I'm saying 4 pi r squared. Again, that's the area of the sphere times its little bit of thickness would be its volume. So that would be a small differential volume times the density would be a certain amount of charge. And then I would need to add up these layers, like layers of an onion. I'm going to add them up. I'm going to integrate these as I go from 0 out to A, and that should come up with my total charge. And so doing that, I've got an expression for that total charge. This is where it can get trickier. Then when we go back, I want to get the R on the outside, or the E on the outside. I will say, okay, again, we've got spherical symmetry. I'm going to go ahead and do that. That's going to be E dot dA.
it's going to be the Q that's enclosed. This side, again, becomes rather trivial. It's just E times the area. The Q we can put in with, that's going to be, I get a little sloppy here. Kind of doing some things. If you stick this in here, I've got a little arrow, and you put it in there, it simplifies. I've got some missing steps. I think you should be able to piece together what that is, and then come up with this expression for the electric field on the outside. So it's looking something like that. Now on the inside, that would be where my R is. Okay, if this is the whole sphere, and let's say I want to go out and get the electric field at some radius here, small r out to here. I want to set up my Gaussian surface such that it's concentric with those and right at that. And so that is my Gaussian sphere. So on the inside, R is going to be less than A. We integrate E dot dA. Again, this just simplifies. This looks a lot the same as before. And then we end up with Q. Q enclosed, though, is going to be a little different. From here, the procedure is the same as it was for getting the total charge. The total charge, I integrated these little interior spheres going from 0 to A. If I'm going to be inside where R is less than A, I'm going to do the same thing by adding up a bunch of layers, but I'm going to stop at R. I'm just going to add them up from 0 out to the R of the Gaussian surface. And so this becomes my Q enclosed. And then that comes in here, and that simplifies to this. So that's both outside and inside. So you can kind of see that Gauss's law we used that. The left side was pretty trivial. On this side, figuring the charge that's enclosed, and this is particularly true with a non-uniform charge density, then you want to be careful. And you probably want to use this method that it's going to be the density times some area, dA, or dV, excuse me, times some area, not the area, but density, volume.
When you're finding the total charge, and you're taking an integral and you're multiplying essentially rho dV, right? Is that what that is?
Right.
R squared is rho.
It would, yeah, it would, yeah.
4 pi r squared dr. Is that supposed to be like dV or dA?
Oh, dV is a layer of this volume. So when we go 4 pi r squared, that's the area of a circle.
Right.
So this little, think of again like an onion layer. This has got some thickness. It's not the whole volume of this sphere. Oh. It's just the volume of that layer. And yeah, that is a key point. And so I'm going to be taking the volume of that as a differential volume is going to be the area of the sphere, which isn't differential, and what is going to be a little thickness dr.
Okay, so you use the equation for surface area of a circle instead of volume.
Yeah, with the volume came in. Let's see, where did I substitute that in? Yeah, when I'm doing this kind of thing, either there or here, yeah, I'm taking the density times, and this is volume. That would be a good thing to delineate here, that this is dV. This is the whole thing is a volume. So it's a surface area times a thickness, and that's the volume, dV. And these are things that typically hang up people, and yeah, I need to make that clearer as far as very clear why I'm doing that and not using a volume. Right, I'm using a volume, but it's a differential volume. Yeah.
2 questions. We're always going to be given that rho is equal to some.
Yeah, he would typically just make something up. He'll say maybe non-uniform. I've got another example that he did on an exam. So you'll see some more uses of that. But yeah, this would be given. Yeah, it's part of the problem.
Where's the, where are you getting the 4 this from, or where's this 5 coming from? A little lost on that.
You mean down here?
Oh, okay, yeah. We've gotten a bit cramped here, and I kind of cut some corners that I shouldn't have cut, so that you don't miss anything. This, though, you should take a look at. Hopefully you can sort this out with you and whoever you're studying with, because this is kind of typical of the kind of problem that he may give you. Okay, other types of symmetry. One is the cylindrical symmetry. First thing is just maybe a line charge. And now in this case, we want to set up a Gaussian surface. Gauss's law is true in general, but we're going to only use cases of high degrees of symmetry. So again, this is cylindrical. We can set up our Gaussian surface. Let's say we want to find the electric field at some r. This is looking down the end here. So out at some r, we've got the electric field pointing out. We're going to set up this cylindrical Gaussian surface like this, so all these electric field lines are out. The charge that's enclosed is just going to be this amount. We've got these end caps. Now, these electric field lines for a very long, or really ideally infinitely long line charge is going to be at right angles to the is going to be just the charge that's inside, and Q inside is going to be just lambda, whatever that is, the linear charge density times L. And so we just deal with that charge that's on the inside. Here, Gauss's law is the same, but again, it's going to be fairly simple. Now, something you want to see that the end caps, and this is really only true for an infinitely long one, where the electric field lines are truly radiating outward. There's nothing cutting through the end caps. So their flux is going to be 0. We're only counting the flux that's going through this cylinder. So that's going to be E dot dA. Again, E and the area are together, so that's going to go out. It's going to simplify to just E times the area of that Gaussian surface. That's going to be 2 pi r. So that's the circumference of this thing times the length. That will be the surface area of that sphere is equal to lambda L over epsilon naught. And then you can see where we're going to divide through and get what the electric field is. So it falls off with a 1 over r relationship instead of a 1 over r squared like it would for a point charge. Let's do one here. This is an exam problem. Okay, now here he's, rather than just a mathematical line charge, he's got kind of a cylinder of charge. Radius A, and it's got some lambda, which is so much charge per meter. And he wants to find the electric field both inside and outside this, and he calls it an infinitely long uniform charge cylinder of radius A, and again, charge per unit length lambda. Okay, so if we go here, this is actually very similar to what we just did. If we're on the outside, I could have actually taken all of this work and really just said, okay, that's the answer. This could be a cylinder, it could be a mathematical line of charge. It's good for either case. And in this case, I got kind of a crude diagram of what we just looked at. And on the outside, you'll find that response, or the answer is the same. Now on the inside, this is where it gets much trickier. On the inside, where r is less than a, we have this, we have Gauss's law, and we want to get Q enclosed. Well, Q enclosed depends on the charge that's inside. That charge inside is going to be the density, charge density, but he gave us lambda. Let's back over here and look at this a little bit. The charge per unit length, lambda, is, wait a minute, it's better here if I just say the charge density, rho, okay, is equal to the charge over the volume. Well, the charge inside here for some length L is just going to be lambda times L. over the volume of that piece, which is going to be pi a squared over L. So this is the volume of the whole thing. So I'm finding the density of the material. Because that's going to be handier for me to use when I go inside. When I go inside, E dot A is going to be the Q that's enclosed. The Q enclosed, this is just this shaded region here. That's going to be the density. Okay, I don't want to use lambda, so I had to take that lambda and figure out what the density was due to lambda. So I use that density times the volume of that inner. That's going to be pi r squared times L. Some things are going to cancel, and we're going to come up with the electric field. This is based on this lambda is part of the answer. So it's partly he gave us a very cryptic way of expressing this charge per unit length. So this is just, lambda is just 1 meter of this stuff sawed off, and say 1 meter, how much charge is in there. That's going to be lambda, but then I need to say, well, I need to get the volume from that and get the volume charge density. So little twists that can really derail people. Yeah.
About the outside of the rod, if it's a charged cylinder, why do we do for the, when we're taking the Q in, why do we do lambda times the length instead of
well, okay, you stated it in terms of lambda, but lambda is just the charge per meter. So if we have some length L, it ends up being just some arbitrary length, that would be the charge for the whole thing. And then to get at the density, I take that whole charge divided by the volume of that to get the charge density.
So for a charged cylinder, it's going to be the same as like an infinite line of charge?
Okay, yeah, if you're on the outside, it's getting charge enclosed isn't too bad. You know, lambda, all you do is take and saw off a meter of this stuff, and that's the charge. And that's the charge that's enclosed. The problem is when you do go inside, now you're just getting not the whole cylinder of charge, but you're getting just a little tiny cylinder of charge that is going to have less charge there because we're dealing with a smaller piece. And so here it's fairly simple, here it's not. I have to say I need to take it times the density times the volume of that cylinder.
I'm just confused because I did the same problem as this where you have a charged cylinder and then you're trying to find the electric field at some point outside of that charged cylinder, and the way the solution had it is for Q in, you do the surface area times the charge density.
Okay, that problem was probably spoken of in terms of the way they state the problem. The way he stated the problem here is that, you know, the cylinder is radius A and charge per unit length L. So when you're doing these problems, he wants it in terms of A and lambda. Okay, but what you're suggesting is probably the more natural way to just look at it from the outside. And it is handy if you have the charge density. That's what he was kind of forcing you to go around to figure out what the charge density is from that lambda. So those things get to be tricky problems. Getting the charge inside is probably the trickiest part to doing all of these problems. Another type of symmetry other than spherical or cylindrical is this planar symmetry. If you have just a plane of charge, again, infinite in its scope, you can get at the electric field if you set up a Gaussian surface. This one happens to be cylindrical. It could have actually any kind of cross-sectional shape and area, but it would be a cylinder that's perpendicular to the surface. We expect from symmetry that the electric field on one side is going to be equal to the electric field on the other side. And so we can use Gauss's law. The charge inside is going to be this sigma, the charge per unit area, times the area. Now you've got some area of these things. There's also going to be an area inside, and that is going to be the charge that's going to be inside the Gaussian sphere. That's So that's the product of those two. The E can come out, again, E dot dA, this is just going to simplify times the area. But we do have two of them. We have a flux going out this way, E times this area, as well as this flux with the electric field going that way. And so we end up with a sigma. This is the charge per unit area, charge per square meter of this material, all over 2 epsilon naught. So. Okay, now we got another problem from this. This is the idea of, he's now playing with this. This is a Dr. Young question. You've got, means a slab of material, non-uniform charge density. Rho is equal to cx squared, where x is measured from the center of the slab as shown. Okay, so something that comes up, this is the x-axis, this is the y-axis. So this positive charge density is equal to cx squared. This equation that he's giving us for the charge density is dependent on x. And some people want to know, well, hey, can I move my y-axis around? But that's going to screw with this thing up. So I mean, you can do it with some u substitutions, but it's best just to leave it where it's at. The origin sits in the middle of the slab. And that's the y-axis, this is the x-axis. Got a little more detailed look down here as far as when we're going to slice this thing up. This is the slab of material, and I've got a bunch of rings of material. I've got my typical ring is some distance x here, and it's got a little dx. Think of like slicing a loaf of bread, cutting these little elements. I use some arbitrary area for this Gaussian surface. I've got it also circular. It doesn't really matter. We can just call it area A. And then there's going to be some charge inside. So let's kind of look at this. The biggest trick in doing this problem is getting that charge inside to do this. And that means that across this slab, we need to do some integration to get how much charge we've got. So the idea would be this individual little piece is going to be this density times dV. The differential volume, that differential volume is of this little slab. And so that's, that dV is going to be A times dx. He's told us that the density is, in the problem, cx squared, so we're putting that in. I'm integrating this thing from one side, which, since this is the y, this is the x, I'm going from a d over 2, or a negative d over 2, to a plus d over 2. Going that way. And if you want, you can easily go from 0 to d over 2 and just multiply by 2. There's a symmetry there. Particularly with this x cubed, x goes negative. Excuse me, never mind. If x goes negative, the density is still positive. Getting sloppy here. Okay, so I can go ahead then and I can do a little integration to get Q enclosed. Once I have that, I really have it pretty well set, because then I can say I'm going to do Gauss's law. The left side is simple. It's just 2e times a. And then this side is going to be c over a d squared all over 12 epsilon naught. And solving for E, we can get, this is the electric field on the outside. And that's true in this direction. There will be an electric field back in the negative direction when you're out in the negative x. And I guess that's where I started to go here with this x cubed. If f of x is negative, it will work out that your electric field will be in the negative direction, whereas out here it's in the positive direction. Okay, how you doing? Okay, so that's an example. Just some things you should know from Gauss's law. Yeah.
Just on the previous example, the dV just was the dx times the area of the cylinder that we were.
Yeah.
Right?
Yeah.
Okay. Cool.
Okay.
add to that, we could take the area out of the integral
Oh.
because it's constant
Yes.
throughout the cylinder.
Yes. Yeah, you can pull that out. I think when we actually do this integral, we can take C and A both out and then integrate that. So I think you'll see the calculus there is pretty straightforward. It's mainly in the setup, and it does give you kind of a look at what he might do as far as adding that added twist in doing problems. Okay, now if we have a metal surface, the idea is that if we take like a charged rod and I touch it to a piece of metal, metal has the ability that the charge can move around, it can conduct. The idea is that the free charges move on the surface and the charges repel. Basically, they want to get out as far away from one another as they can. So they move to the surface. The net electric field anywhere inside the metal will be zero. The idea is we're dealing with electrostatics. When I first charge this thing, there can be electric fields inside and the charges start moving. They're going to arrange themselves and they can be static as long as there's no forces on them. And the idea is if there's anywhere there's an electric field, it's inside the metal. The metal is made up of protons and electrons. If there's any electric field on the inside, the electrons can move and we can have movement of charges. It's not static. So only when it becomes static, these charges line up on the surface. And anywhere inside the metal, the electric field must be zero. Again, if it's not, charges are going to be in motion. Now, also the electric field will arrange itself that these charges will line up so that they will always be perpendicular to the metal surface. The question is, well, what if they're not? What if they're off at an angle? Well, if they're off at an angle, they have a component along the surface. If they've got a component along the surface, the charges are going to move. So this is an important thing we need to keep in mind. That these field lines again will be perpendicular. Now this net electric field is zero anywhere inside the metal is going to be zero, is going to be an important one. One we can do, you had a couple homework problems like this, and this is just kind of summarizes them. Imagine I've got an insulated sphere that's got a charge Q on this thing, and it's inside a metal sphere. And so the metal sphere is hollowed out in here, and we want to get at what the electric field is, let's say, inside. Now, we can play this game. We don't have time to do all of this stuff, but essentially a sphere of charge everywhere inside. We've got a charge Q. We're going to get an electric field that's here. Now, some people say, well, that's inside the metal. It's, well, inside the container. But when I say inside the metal, I mean in the metal itself. The walls of the container, the electric field has to be zero. Now we can use something that, let's say this conductor was originally neutral. I put a charge Q here. Now if I use a Gaussian surface here and embed it in the metal, so here's what I'm going to do. And so the Gaussian surface has to be the electric field has to be zero. If the electric field has to be zero everywhere in this surface, what does that tell you about the charge inside? The charge inside must be zero. So what's going to happen is that this plus Q is the metal, the electrons are free to move. They're going to start to line up and going to line this surface. And the idea is that since inside this Gaussian surface the total net charge has to be zero, this has got to be a plus Q, this has to be a minus Q everywhere on this surface. If these are electrons coming into the center and this was originally neutral, that leaves the outside as positive. Okay, so overall it's got a net charge of zero. You have a homework problem where maybe it comes in with a net charge already. Let's say a net charge of 3Q. Well, this is going to be a minus Q this way, and then we've got to have a plus 3. We're going to have a plus 4Q on the outside, if that's the case. So hopefully that made a little sense. They're fairly easy to do once you get this basic property that the electric field has to be zero inside, and then you can figure out what's happening on the surfaces of that metal. Okay, Okay, that's all I have to say for Gauss's law right now. Okay, again, kind of three symmetry problems, either spherical symmetry, cylindrical symmetry, or planar symmetry. Other than that, he's not going to probably do anything. Gauss's law is true in general for any problem, but in general form, the left side of the equation is just too miserable. If we want to actually do a problem, we'll probably go back to the methods of chapter 23. Okay, wow. Okay. Okay, the next thing is energy methods. Okay, we're dealing with the electric forces and Gauss's law. And energy methods, just as they were back in Physics 121, are generally easier. Do you want to take a little break now, or are you okay? What's that?
Keep pushing.
Keep pushing. Let's get out of here, huh? Yeah. Yeah, I should have. Yeah, it's 123. We run a little. That's why it has the reputation with students as being this is the hardest of the three. Okay. Going back to the good old days of flat Earth, back in 121, when life was nice. The idea that the net work done by a force would be equal to the change in its kinetic energy was part of the work-energy theorem. And so we're just going to take that same idea and adapt it to the electricity and magnetism. The idea of a work done by a force was the dot product F dot ds is, we'd integrate that, is equal to change in K. So we're going to borrow all of this from 121. If we have a conservative force, and this part is a little bit tricky, we define this. This was something that we did back in 121, and a lot of times it doesn't quite catch people till they start to look at it now and they say, where did that minus sign come from? The idea that the change in potential energy is equal to minus the work done. And so the change in the potential energy is equal to minus the change in kinetic. This gets used a lot. You'll see this a lot in the solutions manual for doing a lot of problems. In the past, we'd say, U final is U final minus U initial. Kinetic is K final minus K initial. We need that minus sign so that we can take all the final terms over to one side. This is U final minus K final goes over here as a plus. And then we have U final initial from a minus, take it over here as a plus. And then we've got K initial, minus times a minus is a plus. And this is how we did conservation of energy. We still do. The U final plus K final is equal to U initial, K initial. And it was all we were able to line this stuff up nicely because we made that little minus sign there so that things could juggle and work out fine. Again, saying the same basic thing is that the change in potential energy is equal to minus the change in the kinetic, or vice versa. You can do that. So let's go back to this idea of work done by a force. In this case, we're going to be looking at the work done by an electric force. So that change in potential is minus the work, which is that. And then the work would be going from some point, let's say A, to some point B. QE.ds, QE is the force, dotted with ds is going to be this idea of the work. And so we can go ahead and do this. Now what we'll usually do is take this Q out, put it out front, and then we break things up, and then we do this integral, and it's this minus integral, minus E dot ds is the way we're dealing with the signs. And then we say that, give this a name. We'll call this the electric potential. And I'll put the Q out in front of the electric potential. And the idea is that we can, kind of like the electric field, we factor this charge out, and then when we actually want to get something like electric potential energy that we can use like we did back in 121, that we can just take that charge times the electric potential. So watch the use of the language, the electric potential and then the electric potential energy. So the electric potential is just the potential at some point. It would be like saying, is there a gravitational field at that point? Well, you don't know till you put a mass there. Here we don't have any potential energy. We have, in a sense, we've done all the dirty work ahead of time, doing this nasty integral, and coming up with, we just put a charge Q there, and then we get that total electric potential energy. And so again, the definition of what we're going to say is this delta V, calling it the electric potential, or the change in the electric potential, is going to be this minus the integral of E dot ds. So that's sort of the formalism here. Just in case you missed some of that, the idea of like a uniform gravitational field is a good analog for this, and a good way to kind of make some kind of physical sense out of this. If you have something like a ball or something that's up here and you just drop it, the work gravity does is going to be the force mg times d, and then that should be equal to the change in kinetic. Now, with potential, though, we said, okay, we start with some potential. Isn't the potential energy going down as we drop? Yeah, and that works out nicely when we take the minus for the work done. We can say that the change in the gravitational potential energy is equal to minus mgd. That's the change going from high to low. And something similar applies with the electric force. And if instead of gravity, we've got the electric field and we put a charge here, if it's a positive charge, it's going to move in the direction of the electric field. It's going to accelerate, going to pick up kinetic energy. The work the electric field does is positive. The electric force is going to be Q times Z. That force times the distance is going to be the change in the kinetic energy as it drops. From this definition of the change in potential energy minus the work done, this is where we end up with the change in the potential energy is Q, and again a minus E times D. This is just a simplification of this idea where we're doing this integral. Minus E in this case was just a simple E. It could factor it out in ds, and so it's just a E times some distance. And so that's why we get kind of a simplified version. So again, this is the electric potential is minus E times D, and then if we want to get the electric potential energy, we put that in, we multiply by Q. Okay, whew, okay. Now, what's really important for a lot of problems is what about the electric potential for a point charge? If we have some kind of charge here, the idea of changing the potential, we're going to go from, let's say, from some point A out to some point B. The change in the potential would be whatever potential I have out here minus this. And we need to do that as an integral. E, and we know what E is. That's this KEQ over R squared. And we're going to integrate, oh, I'm getting a little sloppy here. This E dot ds as we go along. ds would be some path through space. And you see that we could actually take any path we wanted to with this conservative force. So this is just the particular one. This is a little ds off in this direction. But we're playing with E dot ds. Now, we can simplify this by saying that E, the electric field, would be pointing out this direction. If we take and we want to dot it with ds that's that direction, we would take it take the product of the two with the dot product times the cosine of theta. And we can see that dr is equal to ds times the cosine of theta. So I'm able to simplify this integral and go from a dot product to a simple scalar here. And you'll notice that the change in the potential really only matters on how r is changing, not the fact that I'm going off at some angle. How does it change as I go from A to B? How, as far as in the r direction, how far am I taking this thing out? That's going to be Here or there we can put in the electric field for some point charge, and we can come up with the change in potential as I go from A to B. Okay? Now, something we're going to do to help things simpler. Remember back in,
Sorry, when you replace ds with dr, isn't there no cosine theta in the original?
Well, this is going to be E ds times the cosine of theta. So ds times the cosine of theta is this, and I can just replace that with dr.
Because the equation up there is as if they were vectors.
Yes. And they are vectors, yeah.
Vectors and the scalars, it's one times the other times cosine.
Yeah, yeah, thank you. Yeah, I kind of bumbled that for sure. Anyway, hopefully you can see that. Now, whether you follow that in its completeness or not, you can still do problems very easily. Now, ultimately, we're always interested in the change in potential from one point to the next, from, let's say, A out to B. Now, usually what we've done in the past, like in Physics 121, we make a zero potential. Usually we'd say, okay, where is the potential energy zero? We say, oh, well, it's the ground or the tabletop or something. When we do this, it's handy to a natural way to do this mathematically is to say, when is one of these terms zero? So if we're going to make a change from, let's say, make V sub A, well, I want that potential to be zero. If I look at that term, when is this term going to be zero? Is whenever R is what? Yeah, when that is infinitely large. And so this is going to be the natural place for us to place our potential energy zero. This is important to see as far as doing problems. We're going to say that V is equal to 0 at R is equal to infinity. And then if we do that, we can write the potential like we did before, where we assume the potential on the ground was 0, and then we say the potential at some point, or potential energy, was rho GH, we'd say. That was measured reference to the ground. Here we're going to do our measuring, but we're going to do it in reference to a point out at infinity, whether it's a plus infinity or any direction we go. Then we can write the electric potential is going to be KEQ over R, and do the problems that way. Let's put this to use. Okay, looking at electric potentials for a positive charge, they go up as you go out to infinity. You can look at and for a negative, they're going to tend to drop. A close thing with this is the idea of electric potentials, equal potentials. Here, the idea of, think of like a topological map where we cut this thing. These are at the same heights, and therefore anything around here is going to have the same electric potential. We can do this in kind of a 2D look as we look at this. Anywhere around here is an electric equal potential. So the idea, if I'm going from some point over to some other point, like we're looking at here, all that really matters is the change in potential is how far I go out. And if I end up out here, I could go from here all the way out to here and down and around. All it ultimately matters is how it changes in R, and the path of integration doesn't really matter. Okay, this was another test question. Okay, as 4 protons are held together in the corners of a square measuring 1 centimeter on the side. If one of the protons is released and flies very far from the other 3 protons, what is the speed of the proton when it is very far from the other 3 protons? So I've got my protons arranged. I just call this distance A, just for, I don't know why, I think I stick in the numbers anyway. Anyway, that's going to be 1 centimeter is going to be that. I'm going to focus on this one. And what we want to do is we want to use energy considerations. So the idea is, first, I want to get the electric potential at that point. So imagine that's just a point in space. I could even take that charge and lift it away, and that point is still there. And then I can get the electric potential. Once I have that electric potential, I can take it times the charge of the proton, and I can come up with a potential energy. So break it into two of these parts. Just a point in space, what is its electric potential? So I can get the potential at that point. Now it's due to these other charges that are present. So again, lift that charge away, and at this point in space, these two are the same distance away, so the potential is 2. Wow. And this other one is further away by root 2a, and so it has that difference here. Notice that there was no components. We did that kind of similar one earlier where we had components when we were dealing with forces. You know, this one had a force in that direction, this one had a force in that direction, and we had to deal with all those components. Nice thing about the energy methods is that they're just scalar. And so if I add these up, these are these two corner charges, just times 2 because they're the same distance away. This other one is this distance, we can add that. We can do the math, stick in the numbers, we can get the electric potential at that point in space. Then we can get the electric potential energy by taking the charge times that electric potential. And looks like I crunched the numbers there too. E would be 1.6 times 10 to the minus 19th times that number, and we get this as the potential energy. Okay, so that is potential energy at that point. Now what we're going to do is when the electron is very far away, that is the change in the potential goes to 0, or excuse me, the potential goes to 0. The change in the potential goes from this to 0. And in that same process, the change in the kinetic energy is going to go from final minus initial, so the initial is 0 up to some final value. So for conservation of energy, I'm expressing it here as you see it often done in the book, as delta K is just equal to minus delta U. So it went from this potential energy down to 0, and then the kinetic energy went up from 0 up to that. And so when it's very far away, i.e. infinity or close to infinity, it's going to have this velocity, 8.64 meters per second. A little added twist on that. Say, well, whoa, what if all the protons are released simultaneously? In the previous problem, we just let one fly away. These other ones were kind of like they're glued in place. But they also have some potential energy with them. And so if we say, well, let's say we're going to release all the protons, they're all going to go flying off. It sort of makes sense to all contribute with the sharing of the energy. But what we need is the potential energy of the complete system. And we'll start with all the protons at infinity. So the idea is, if I want to come up with the potential energy, I can come up with the energy. Ultimately, this thing is going to blow apart, but I'll work it backwards. I'm going to just bring them all in from infinity and bring them in one at a time so I can keep track of things. What I'm doing here first is I'll bring this charge in, nothing else present. I just bring that charge in from infinity. I'm not bucking any forces, so that potential energy is just 0 for that first charge. Then I bring in the next one, and I guess I've got B I'm going to bring in next. I bring it in from infinity, but now this one is fighting A. These other guys aren't there yet, so I'm just fighting A as I bring it in. It's no longer 0, but when I bring it in, it should go from 0 out at infinity all the way to Ke squared over R. So that's that energy for that one. Then I'm going to bring in another one. I'm going to bring in C. So now that C as I bring it in, D's not there yet, but it's going to be bucking these two as I bring it in. And so I have these two. This is
this is going to be the potential energy of C is going to, A, yeah, it's not fighting D yet, so it's fighting A, that's this term. And then out here with B, that's with this distance here, square root of 2, we've got that. So we've got that. And then when I bring in my final charge, I have these 3 charges present, and so I bring in my final charge from 0 all the way to that point. And so it's bucking 2 of these ones that are just a distance A away, and then also this one that's across here. So when I bring all 4 of them in, I add them one by one, and the total energy required to pull them all together is a potential energy. This thing wants to explode apart. And so I add these terms up, and I come up with the potential energy, not just of the one that was sitting here, but all 4 of them, the potential energy of the entire system. So now when I put it back in there, I've got that. Now if we release them all, we're going to unleash this energy. It's going to be final minus initial. They're going to fly apart again, so they're going to go out to infinity at 0. And that should be equal to minus the change in kinetic energy. And that's going to be, we have 4 protons. They're each going to take off with 1/2 mv squared. They're going to start from rest, get up to, and so we've got 4 kinetic energies. We have the mass of the proton, and we can come up with the velocity that they're going to take off. Now this, compared to the previous problem where we just released 1, that one took off faster. This one is each one is slower, but we have all 4 of them that are moving out. So this is kind of how you play this kind of a game.
We got a couple questions.
Yeah. Yes, I'm sorry. Yeah.
The velocity that we calculate is in the different direction for all of the particles?
Yes, yeah, okay. Right. The thing is, with energy, it is a scalar and it delivers a scalar.
Yeah.
I am using kind of symmetry, and my picture looks kind of bad here, but these should be taking off as a diagonal. And we would just use a symmetry argument there and say, hey, they're going to be going out radially from the center. And that's how I would specify that direction. Because again, energy is strictly a scalar, and we may have to use some kind of symmetry argument to say, oh, but the direction has to be, yeah.
So like conceptually approaching this problem, we imagine that they're all very far away, and then we bring them in one at a time, and you calculate when you bring them in.
Yeah, right.
You bring the second one in, and there's only one other.
Yeah. So exactly right. Yeah, in a sense, we're going to think of like cocking this thing. We're just going to pull this stuff together, and then we're going to release it. Now, by figuring out how much energy did I have in this bomb before it goes off, I did this systematically where I assembled it one charge at a time. When I release it, I'm going to let them all go at the same time.
I'm just confused on like our energy equation for D, why it's going to be 2UD instead of 4 times UD.
Okay, well,
because in my mind it's like each one is having the same equation that UD has acting upon it.
Yeah. The thing is, these potential energies are shared between particles. We don't say, like if I have 2 point charges, I don't say that the potential energy of one of them has all of the potential energy. It is shared between the 2. So they are all shared. We have a sharing between all of these. This first one didn't have to share with anything and doesn't require any energy. Then when I bring in the second one, I've got 2 charges, and this energy is really shared between them. It's part of the system. And then when I bring in the third charge, it's shared with the other 2. And then I bring in the fourth one, it's shared with the other 3.
And so this is, again, the total potential energy of that system. And so I just took this methodical way of assembling this thing, and then when we release it, we're just going to release it like a bomb where they're all going to go off and take off.
Would it be correct to say that, because the way I'm thinking of it is, you have UD as the equation for the 3 particles acting upon 1. You do that by 4, you multiply that by 4 for the 4 particles, and then since for every reaction there's an equal and opposite reaction, you divide it by half, because if one is going to push out this way with that much energy, it's also going to push the other one out that way, so you divide by 1/2.
I think no, I don't. As far as answering your question succinctly, you want to keep in mind that these potential energies are shared between these two, and you can't say one's got more than the other. It is, I guess I'd have to give a little more thought to your question. You've had your hand up.
So you use a different method to calculate the potential energy. Does it matter which method you use? Before you, like for the particle before for number 1, voltage.
Yeah, now the previous problem, all I worried about was the potential of this guy up here, right?
Okay.
Now that was tying together these other charges, so that part was the same. But what I didn't even address here was, hey, there's potential energy between these two and also between these two. And we don't use that. Now, in terms of energy principles, all we really care about is the changes in potential. So before I released that guy, there was some potential energy between these guys, but yeah, it holds both before I release it and after I release it. So that potential energy, even though it is there, I don't need to include it because it's not part of the change in the potential.
So could we use that method where we're summing it here?
Yeah, what we would end up with as other terms would be these potentials between these two, and they would stay on the before side, initial energy, and they would also appear on the final side, final energy. Since they're going to be the same, they would just end up dropping off from the equation. So you could certainly include it. There would be nothing wrong with that if you want to. And does that make some sense? Yeah, some subtle issues, but these I think are important. That's one reason I threw this in here. And okay, yeah.
Why are you squaring your E's, your charges on the second column, not the first one?
Oh, okay, yeah. Very good question. On the previous problem, I did electric potential, and then I stuck in the E here. Okay, right. And what I did on this one, okay, good, very good point. These are not the electric potentials. I'm going with electric potential energy, so that includes the other E.
So is that like the V? Is that are your U's the same as V?
This should be equal to E times V. So what I'm doing is, rather than write V's here, I'm automatically sticking in the E in there.
So you can go straight to velocity without having to
Right. Yeah. I want these in potential energy, and that electric potential, and then put the charge there for electric potential energy. Yeah. Okay. You're all asking excellent questions, and I realize this has got to be cleaned up a little better. Whew. Okay. Okay, now something that works out nicely, getting E from V, that is, if you have your electric potential, what I want to use and call on, something you've seen dot products, and I'm sure you've seen this before, is if you got the dot product between two vectors is A, B times the cosine of the angle between them. If we break this up as far as B times the cosine of theta is going to give us some component of B along A, parallel to A, we just need to say A times that parallel component. Same thing applies if we want to take A times the cosine of theta. A times the cosine of theta is A parallel, and we just take it times times B. That hopefully you've seen that idea, but think of that idea in terms of getting the change in potential. Formally, we write the change in potential, which is really just adding up a bunch of potentials, is equal to this minus E dot ds. Okay, so this is, now what can be helpful for us here is to see this, we say, in differential form. The idea that we're doing a bunch of integrals, delta v is adding up a whole bunch of little dv's, and this is adding up a whole bunch of these little dot products. If we just say, well, let's look at what we're doing one step at a time. We're going to say the little dv is equal to what's inside here. And of course, we can then go ahead and take the integral and get it in its more familiar form. But this alone is what we call just the differential form of that. You take the electric field dotted with some little tiny displacement. That's going to lead to a little tiny change in potential. And we can take advantage of this. If I take the dot product, this is where I want to use this idea. I can say that ds, I can choose a number of ds's. So let's say we've got in the xy plane, we've got some point in space, and I figure that there's some electric field, let's say, at that point, and I want to get at it. But all I know is the potential. If I take the potential and I take a step, let's say I decide to go in the x direction, instead of just arbitrarily in some ds direction off in space, let me go in the dx direction. Then I can say, well, the dv in the x is going to be E dot ds is going to be just dx times I hat. And then this dot product is just the x component of E in the dx direction. The x component of E in that direction, and then we can say that, well, the product of that, we still have that minus sign. Then we can say that E in the x, we can just divide V in the x divided by dx, and that leaves us with this differential. Formally, those that have had advanced calculus and are these strange-looking partial derivatives, the idea that there's different ways of getting at a greater number of variables than just x, and this is how we usually express it. If you haven't seen this type of thing before, don't worry so much about it. But the idea that we can take the derivative of this with respect to x, and we can get at the x component. If we want to get the y component, we can use our ds. We'll step in the y direction, and that's going to be in the dy. And so ds is equal to, choose a path. Oh, did I? Well, okay, this is really getting at it, what I want. My ds is really dy j hat. I'm going to take the dot product. I'm going in the y direction, and so E in that direction is E sub y. And so we can do a similar thing with dv, dy. We can get that. We can even do it in the z direction. It doesn't show in the diagram, but we can do that. And we can look at these as giving our components, our x component, our y component, and our z component. Okay, now doing this is a powerful way of getting the electric field from the potential. I don't want to do too much here in detail. This is going back to the ring problem, which we dealt with earlier, where we dealt with forces, and remember that was that little cone of forces. We had to do an integration. Got a little messy. Potentials are a lot cleaner, and that's one reason that it's nicer to use. Usually energy methods work better. So the idea, if we want to get the electric potential at point P, we have let's say a charged ring, and it's made up of a bunch of charges, a little dq. And the idea that there will be some, this is the idea of the potential of a point charge. And I start with that. I say, well, there's going to be a small little potential at this point, due to the fact that there's a small little charge up here, dq, so I'm doing that. I need this R value, the distance from that charge to this point, to make use of this. And that R value, Pythagorean theorem as it was before, a squared plus x squared. So we can take that R value, put it in here, and the integral is fairly simple. We've got this. We've got a dq. And again, as the argument was before, that as far as we're integrating around this thing, x doesn't change, a doesn't change. And so that there's all this, in case of e doesn't change, we can take that out. And then we're just integrating dq. And why make life difficult? That's just got to add up to the q of the ring. So we can get that electric potential. Now this was a lot simpler than what we did with vectors, where we had to deal with the components. We could deal with the x component, the y component. We had to integrate around it. Same kind of integral there. It wasn't too bad, but this is the would be the potential at this point for this ring, some distance x from the center. Okay, and then if we want to find the electric field from the electric potential. Now, here I'm interested. I know this electric field by symmetry. It's got to be in the x direction. So here's where I'll make use of this. I can take the derivative with respect to x of this expression. And when I do that, you can look at the math. You're going to come up with an expression that I want you to compare it to the method that we did for direct integration with E, with the components. We're going to get the same answer. So this is just an example of using this, the potential, or derivative for potential, to get at what the electric field is. Okay.
Wait, I have a quick question about that. Why did we... I understand how we changed r to square root of a squared plus x squared, but why did we do that? Because we end up with the same thing. Can't we just say r, because r is a constant?
Oh, yes, you could do that. Yes, you could do that. Short answer.
But if like p was at a different point, r would be variable.
Yeah, it would change. It's really depending on x. I guess to do this, I do want it as a function of x. And so if we used an r instead here, that is a function of x, and so it's not going to like go away.
So we use the a squared plus x squared square root because r is a function of x.
Yeah, okay. Yeah, while you mentioned this is a good point. Before, when we integrated around this thing, I was integrating around this thing, and all I said, hey, I just need to integrate a bunch of dq's. I've got a q. Now when we do this, we're changing x. So now x, instead of being a constant, was constant for this integration, but now we're going to let it be a variable. In a sense, we're going to take a little step in the x direction, and we're going to see how the potential changes. And the faster it changes, the stronger the electric field. And so I do need to take the derivative with respect to x, and so just saying, oh, that's r, and r is constant, okay, r was only constant for this integration. Now it is a function of x, and so we're stuck with that. Okay, good point. Yeah.
Where did that 2x come?
Oh, when I'm taking the derivative, it will be a chain rule. We get this to minus 1/2 comes down, then minus 1 becomes 3/2. But then we have to take the derivative of this, and so that's going to become a 2x.
What about the last equation? Where is
2 goes away with the
Oh, boom. That knocks off, and the minus signs knock off. Okay. Yeah. So I'll let you check if you spot any other errors. I know I made that one earlier. Let me know. I'm not going to take the time for this, but you can play the same game way with the disk. Maybe go through this, see if you can piece it together. If you got time, you got nothing but time, right? You can use the energy methods to do the same thing. So let me just let that one slide. Okay. Now this one is, how are you doing? Do you want to take another breather, or just plow through? Just, okay. Okay, this is similar to the problem 3 we did earlier. A charged sphere insulating material has a positive charge density rho. Okay, it's going to be uniform. and has a radius. Okay, you can read this. If a proton is released from rest near the center of the charged sphere. So we've got, think of that charged sphere as like a cloud, gas cloud, that the charge can be in there and it can start to take off and will just cut right through this cloud of charge, and it's going to be repelled. It's a positive charge, and it's going to be repelled by the positive sphere, and it's going to start to accelerate. So the idea is we can go back to this idea of the change in electric potential would be based on, now as it takes off and goes out here, it's going to accelerate. It's feeling an electric force that's going to be increasing as we go out, and then when it gets on the outside, the electric field is still going to be driving it. It's going to drive it all the way out to infinity, but it's going to be falling off with the inverse square. So the idea is we want to go from 0, from the center of the sphere, on out to infinity, and we want to use this relationship we've developed for the change in the potential. And we need to break this because there's a discontinuity in the electric field. Should I put up another one here? That it was going up linearly till it got to the edge of the sphere. Then it fell off with the inverse square. So I'm really doing kind of two regions for this. This is while it's inside. We've got this relationship. This was the electric field. Excuse me, this whole thing was the electric field times dr. And then we're going to integrate that from 0 to a, the edge of the sphere. Then we're going to go from a all the way out to infinity. So that would be using the inverse square. So I've got really kind of these two regions, one region and the other region, and I'll add those two together to get the change in the potential. Then I can say, well, if I have the change in potential, that's the change in potential from here all the way out to infinity. I've got that. The potential, and then I can go to the potential energy of the proton. So this is where I'm kind of breaking it into these two parts. This is the electric potential. What I want is the electric potential energy, so I have to multiply by E. And so I'm going to end up with this. Did I drop an E here? Oh no, we had this. The other dropped out. That's right. This was the density. This was the original charge, and now I'm sticking in a proton. So that is okay. And then we use the idea of conservation of energy, that the change in potential energy is equal to minus the change in kinetic, and we can get from that change in potential what the kinetic is, and then what the speed is for that particle as it goes out to infinity. Okay. Let's see. I have another one. Let's see if I can. Maybe they're moving on. Oh, whew. Okay. Nobody's been on this side yet. Usually they get started over here. Okay, this is an alternate way where we just say, okay, let's say solve it slightly differently from the center of the sphere. The idea is, say, right at the center, I say, well, what is the potential there? And the idea is that what is the idea? Oh, I don't know. Oh, okay. I'm getting the potential at this point, and I'm using. Now let me leave this. We've got a lot of ground to cover, and it's already a little after 4. Boy, went off on this thing at home, and now I'm just kind of drawing a little blank here. I think this is stopping. It's just an alternate way of doing what I had just done. Okay, the idea is that, yeah, I want to get the potential at a point. This is just the potential energy of a point charge. And, oh, okay, what I'm going to do here is I'm going to get a little spherical shell of charge. And that's going to be the density times 4 pi r squared dr. So the area of that sphere times the thickness again. So think of like layers of a nested onion. And I can then get the potential. I'm going to integrate that from 0 out to a. So I'm going to take all of these spheres, kind of like I was doing before on the one problem previously, where we have to just add up all our potentials for this. So I'm going to add those all up by taking the integral of the V is going to be k rho times 4 pi r squared is going to, and this is going to be a volume, so that is going to be a charge times r. So basically I'm still coming back to that of a point charge, and I want to get the potential for that. I'm going to integrate all of these potentials, so basically I'm getting that energy just to put this thing together. I'm going to integrate it from 0 out to a, and then this represents the electric potential, and I'm going from 0 to a, so this is the electric potential at that point. So if I take that electric potential, yeah, V, okay, and that should simplify to this, okay, made total sense to me at the time. And then I can get the potential energy by just multiplying this through by E, and then playing the game again. What is the change in the kinetic energy is equal to minus the change in the potential energy. Our change in kinetic energy is going to go from final, which is going to be 0. Wait a minute, that should have been the other way around. Should have been final here, 1/2 mv squared over initial is 0. And this is the potential energy before. This is actually before, and then after goes to 0. I turn those two terms around. I better go back with a red pen on this one. Maybe I'll just sidestep this for now. Let's do something with capacitors. Okay.
So wouldn't the proton want to be in the middle of the sphere?
Oh, that is a good question. Yeah, it does want to stay in the center of the sphere.
So
Why would it ever leave? Now, it's what's called an unstable equilibrium. The idea of something like, if you've got an example would be, let's say you have a hillside and you've got a ball perfectly balanced up on top. It's going to stay there, right? If you give it a little tweak, and once it gets rolling, it takes off. So the same thing is happening here, where if you've got this cloud and it's here in the center, the forces are 0 on it. It does want to stay there. But you could tweak it, and you could tweak it in any direction. So if you tweaked it slightly this way, it would take off in the x, or if you pushed it that way, it would take off in the y. So but it is what we call an unstable equilibrium, that it's just balanced there, the slightest perturbation, and it takes off.
Would that change if the charge on the outside of on the sphere was higher?
It might change in amount, so with, you know, how stable it is. Yeah, it's.
There's no way to make it a stable equilibrium?
A stable equilibrium is usually viewed as like a valley, and the ball is here. A stable equilibrium, if you tweak this thing off to the side, it rolls up and it comes, you roll it right back. So it keeps wanting to come back to the bottom. Unstable equilibrium, it's ready to take off, and I just tweak it and it's gone. So this is an example of an unstable equilibrium. That often confuses students, and they kind of lock up on the problem.
I understand the equilibrium, but it's just like, is there ever a situation where a like charge, the like type of sign of charge is inside a thing where it's stable?
Well, I'm thinking.
It's a broad question.
Yeah, it's a broad question. I'm thinking that if we're dealing with all positive charges, we're okay. We could, let's say, of a sphere, if this is a positive charge, an electron sitting at the center would be stable. So it's got negative. You displace it, it flies back, and so.
But if it was a conductor, maybe then it would be. Instead of an insulator, it would not be unstable.
Boy.
The charge would move around in response to the proton moving.
Um,
Can you keep it inside, sort of?
Yeah, I could maybe. I would have to give it some thought to. Yeah, you're asking a broad question that I'm not quite sure how to answer. Okay, capacitors. Let's get at least a little more nuts and bolts here as far as what we're doing. The idea of capacitance, the definition of capacitance, Q over delta V. The idea, simplest one is like a parallel plate capacitor. The idea that we can connect this thing to some potential, like a battery, and these are charges, negative charges can flow up on the plates. That's going to drive electrons from this plate over to this plate, and so we're going to get an overall flow of electrons. We're going to build up charge on these things, and we've got these plates and the plus and the minus. We're going to set up an electric field that's going to be on the inside of this thing. And the idea that we put a certain amount of charge on there, this forms the definition of our capacitance. How much charge do I put on versus now what is the electric potential? Now you're going to see that I've got absolute values. Capacitance is always a positive number. The charge has got a plus on one side and a minus on the other, so we just put the absolute value of the charge on this thing. The delta V is the potential between one plate and the next. We can do that by integrating across here. This is, since it's a uniform electric field, we can integrate E dot ds as we go across this thing. Okay, let's look at that detail. Let's do this particularly for a parallel plate. The idea that the electric field that's going to be on the inside, kind of this picture, electric field in here, is going to be sigma over epsilon naught. We can get that from Gauss's law. You can think of it also as two charged plates, one plus, one minus. They're both contributing to the electric field. And this is the electric field inside. That's going to be the sigma is going to be Q over A over epsilon naught. And when we go to the idea of the electric potential, all I care about is the absolute value, so I'm just going to drop that minus sign. It's going to be E dot ds. This is just, since it's a uniform electric field, this just simplifies to E times that distance d across the plates. That gives us the voltage here, the difference in potential between the two plates. And then what I can do is go back to my definition of capacitance. It's going to be the Q over the delta V. Delta V is, of course, this, and I can go ahead and put that in. And the Q is going to drop out. It doesn't matter on the amount of charge that's there. The more charge I have there, the more delta V I have. And so the two are going to go up hand in hand. They're both related to Q. That's going to drop out and going to leave us with the capacitance of A epsilon naught over D. And so this is our kind of our classic parallel plate capacitor we do a lot with. And so that would be kind of the derivation of what would happen if we're going to charge it up using this definition of capacitance. Okay, we can also look at the energy that's stored. So kind of between the two plates, we have this electric field. This is coming off the plus plate and going into the minus plate. And if I've got a certain charge, let's say dq, and I want to charge this thing up, is the idea.
the idea I'm going to take a charge there. Consider it kind of like the assembling of charges that I did earlier, bringing them in one at a time. What we can do is we can charge this thing up, start it with no electric field here, and I can take a little dq from what's going to become the negative plate, because I'm going to take a positive test charge and I'm going to move it across this plate, little dq. The first bit I bring across, it's not bucking anything because it's got, there's no forces on it. I can bring that across easily. Then as I start to bring these charges across, I start to build up charge on this thing, and the electric field gets built up. And the little bit of change in electric potential energy will be equal to the charge, or the potential between these two plates. It really actually should have had a delta V there, the difference between these two, times dq. And then to get the total energy, what I'm going to do is, again, bringing these across, I keep building and building the charge here. As I do that, the electric field gets stronger, the electric potential difference becomes stronger, and it becomes harder and harder to bring these things across. But the idea is I would add them up as I bring them across one by one, and I'm going to charge it from 0 up to some capital Q, and the capacitance is defined to be Q over V, or V is equal to Q over C. So if I use this expression in this thing for V and integrate, so I'm going to integrate that from 0 to Q, I end up with potential energy in that capacitor is going to be 1/2 Q squared over C. So this is the actual energy in the capacitor. This is kind of the easiest way to calculate it. More conveniently, we often say that, oh, but Q is equal to C times V, going just back to the basic definition of capacitance. And so that also reduces to this form. So these are really saying the same thing. But this is the easiest one conceptually to get at. This one is probably more useful as far as the energy inside. Something we'll look at and play later, more in the later part of the course, where we can talk about energy density, and that's where we take that energy. When you look at this field here, we say, wow, how much energy does it have? And we get energy density. We take that whole energy and divide it by the volume. Volume of the capacitor is the area of the plates times D. This is the energy density. And then also V is equal to E times D. And you look at some terms are going to cancel and simplify. This is going to become a D squared. It's going to knock off with this one and this one go out. The A's are going to cancel. All of this, convince yourself, is going to be simplified to 1/2 epsilon naught E squared. And so that is what we'll call the electric field energy density. So if you're wondering, this potential energy, often where is that potential energy? Where does it hold? It's in the electric field, and this is suggesting, and we can do a lot more with this, and will later, as far as coming back to this idea of the energy density of the electric field. And that's the actual storage of energy in the field itself. So that's got some exciting prospects for the future, but enough for right now, right? If you need to calculate let's say the cylindrical, coaxial capacitor, it'd be like a couple cylinders. We have like inner cylinder, could be a metallic surface typically, and will be for this, and another metallic surface. Here's looking down the end of it. Now, inside here, we know that the electric field, we could do a Gauss's law inside here, and we end up with lambda over 2 pi epsilon naught r, where lambda is Q over L. So we're going to take a certain length of this coaxial. It could be a coaxial cable, maybe, some length L.
And we want to get the capacitance of that. First, we'll get the delta V. The delta V is going to be the integral of E dot ds, and with this E, we can integrate that, and we come up with the delta V between the inner surface and the outer surface. So that delta V between those two, between A and B. And then, once we have that, then I can go back to the definition of capacitance. It should be Q over delta V. So if I take all of this and stick it in here, this Q was hypothetical. It was a certain amount of charge that's on there. This is going to go out. This capacitor, it doesn't matter on, it stays constant. So if Q goes up, then V goes up. So they both go hand in hand. And they will end up dropping out. And so this is the capacitance of the coaxial cable. Something that is done here often with the coaxial cable, we have the length of this thing. We can bring that over to the other side. Very often we express the capacitance per meter for something like a coaxial cable, capacitance per meter, and we have and anyway, this would reduce to that, and so this is the kind of the derivation of the coaxial cable and its capacitance. We could do the same thing with a spherical capacitor, same basic thing. We get the electric field inside, we get the difference in potential. Ultimately, what I'm looking for is the definition of capacitance. I put some charge on this thing. I put a plus charge here, a minus charge here. There sets up an electric field. Once that electric field's set up, I get a change in potential between A and B, between this surface and the outer surface. And with that delta V, then I can plug that back into the capacitor equation with a delta V along with the Q. The Q's invariably cancel, and that just leaves me with the capacitance, and this would be for a spherical capacitor. So you take a look at those. So those are some examples of calculating capacitance. Okay, wow, something that you're going to need to do as far as speculating on what kind of problems they're going to do, he's going to do. For sure he's going to have some capacitor problems where they're connected. We want to look at, first of all, let's look at capacitors that are connected in parallel. The idea that if I have a voltage source that's going to provide charge, that's going to build these as charge, we put these two capacitors, we say in parallel. This is a connection, the way we're connecting these things. I come up here, I connect to this one, and I also connect to this one and this one. Now what's this going to do as far as charging this thing up? The idea these negative charges can come off of here. They can come onto this plate. They can also split and go onto that plate. So both of these can hold charge. We say it's got a total charge of the sum of these two charges. And then on the other side, when we bring an electron in here, that's going to drive an electron out there and back to the plus side. Same thing up here. And so we're going to end up on charges on both of these. And something we like to do is come up with, this is kind of the symbolic form of this. The parallel plates are indicated this way. So this is just this kind of picture with using our circuit elements. You want to get used to seeing these. The idea that we can take these two capacitors together and we do what we call a C equivalent, an equivalent capacitance. We replace these two with one. And it's going to turn out that it's going to be just the sum of these two capacitance. We can do that as far as looking at this idea. And this idea is important, that the total charge that we put on this thing is just the charge that we have on these individual capacitors. Since that's giving us an equivalent capacitance that's holding this amount of charge. And then each of these, we can say that Q is going to be delta V over C. So that's just using our definition of capacitance. And
Q is delta V over C1 and delta V. These voltages across here, whatever, let's say this is a 12-volt battery. This is going to be 12 volts here. It's also going to be 12 volts there. So the voltages are the same. The capacitance, as far as the equivalent capacitance, it's the same as adding these two capacitors. So this is kind of the easiest one to manipulate. Two in parallel, they're just going to add together. Now, this is important as far as doing problems and kind of reasoning out what's happening here. In parallel, the charges just add up. Okay, so they both hold charge, and that adds to the total charge. But the voltages are the same across these. They're both connected to the same battery, and they both share the same voltage. So this is an important idea, and we need to be able to reason like this. Now, if we connect a couple of capacitors in series, one and then the other, this is kind of what kind of the pretty picture. This is the symbolic form which you want to get used to. When we do this, now when they charge, the negative, the electron can come around here and go to this plate, making that plate negative. That's going to drive an electron off of this plate and run it over to here. When it runs over to here, that will become negative. It also wants to get it away from this other negative here, so it's going to drive itself as far as it can. And then it's going to drive an electron off of this plate over here. So it's going to be minus, plus, minus, plus. But they're tied together. When they're connected in series, one to the next to the next, the charges will be equal. That is, whatever charge I put on this is just going to drive the same amount of charge onto this other one. And so we say that capacitors that are in series, the charges remain equal. However, if we look at the voltages, there would be, from the plus plate to the minus plate, there'd be an electric field in there, and there'd be an electric field here. So if we wanted to get the potential, we could say we could integrate across here with the electric field. There will be some delta V1 here. That's the voltage across these plates. And another delta V2, the voltage across these two plates. And then we're going to just add them together, and the addition of these two should equal the voltage on the battery. In a sense, this voltage is being divided between these. So in series, it's important you get the idea that voltages in series add, and when they're in series, the charges will be equal. So this is important. As far as coming up with two capacitors, we can come up with an equivalent capacitance. The idea that the voltages are the same. The voltage across the equivalent capacitance is just delta V. But when we add up delta V1 and delta V2, they should add up to the source voltage or the voltage of the battery. From those individual voltages, it's going to be, well, the total charge Q all over C equivalent. And then there will be V1 is going to be the charge Q1 over C1. And V2 is Q2 over C2. And all those Q's are going to be the same because they're in series, so that they can cancel. And then we're left with this kind of messy equation that deals with capacitors that are connected in series. Now, in series, the charges are the same on both of those capacitors, but the voltages will add as we go across there. Okay? Whew.
So, in series, the charges are the same, the voltages add, and then in parallel, the charges add and the voltages are the same.
Yeah. So parallel, the charges add and the voltage are the same. Okay, and then in series, the charges are the same, but the voltages add. Okay, so hopefully I'm kind of ripping through this, but hopefully you guys have learned this stuff pretty well, or will. Okay, he's got problem number 8. actually, I've got some of this work. It is number 8. I don't have the text with that right now, but essentially, I can guarantee you're going to get a problem like this. He's going to give you some connection. We've got a battery where the plus and the minus, and these are the capacitors. And he gives us values, 15 microfarads, 20 microfarads. You can read these values here. And what he is going to want is, he says, okay, connect all of that to a 20-volt battery. What is the voltage and capacitance of every single capacitor that's there? In charge, yeah. Charge and voltage, okay? Now, so this is kind of the picture that you get in the problem. This is my extra stuff. Okay, now when you want to simplify, we want to first kind of simplify this thing. And the idea is, start with a big picture. Get a big piece of scratch paper. Because you want to draw this thing out, and then you want to start to simplify it. Now, I look at these two. Can you see that they'd be in series? Okay, yeah, whatever charge is coming into one is going to come off and drive over to the other one. So we can replace these two with a C equivalent. I say C equivalent 1. So this circuit just becomes like this. I hope you see that. Just combining these two. And the idea, what I'm going to do is I'm just going to keep simplifying until I get a real simple picture, and then I'm going to end up working backwards to actually answer the question. So that's why it's good to lay these out and try not to cut too many corners, because it's easy to drop some term. It's the equivalent for this is, since they're in series, it's 1 over, and here I'm just putting 20. This is microfarad. It will turn out that all of these are going to be in microfarads, so you can take a little bit of a shortcut there. I just have 1 over 20, implying that they're all microfarads, 1 over 10, 1 over C equivalent, and I come up with C equivalent for this first one is 6.67, and that's microfarads. Then what about these two? These two are in parallel. Okay, so since they're in parallel, we can now take this picture between this one and come up with another equivalent. So just crunching these down as one capacitor. The only one left over here is C1, and it's still there. So I can get C equivalent 1. Now the nice thing about things in parallel, you just go ahead and add them up. So it's 10 microfarads, and C equivalent was 6.67 microfarads. So I get 16.67 microfarads is the equivalent capacitance. Then I can say, well, these two are in series, so I come up with an equivalent capacitance there. Again, it's a 1 over 15. This was 15, and this was 16.7. And okay, now watch your math here. Be careful. Solve for C equivalent, and I get that. Okay, so once I've done that, simplify till I'm down to a voltage and a capacitor. Now I want to reason this thing backwards to answer the question. So I consider that I did this move. Now I'm going to go backwards. I'm going to start here where it's simple, or relatively simple, and start to work backwards. I think I've got this in blue to just kind of indicate my new work. I can get the charge on this thing. I've got 20 volts. I just need to multiply that times the capacitance. Okay, now I've got 7.9 microfarads, so that's going to lead to a microcoulombs if I get slick with my units. Otherwise, they can get kind of messy. So I've got a C equivalent, a Q equivalent, a charge on here, and that's the total charge that's on this whole setup, is 158 microcoulombs. Then once I realize that what this charge is, then I can go back to this step and say, well, let's see, the two of these are in series, so what about the charges in series? They have to be the same. So I know that Q1 has to be 158 microcoulombs, just like that, and Q equation 2, the equivalent one here, is 158 microcoulombs, so I have that.
once I have the charge and I have the capacitance, then I can also get the voltage. This previous one had to be 20 volts. Okay, so that one. Here I go ahead and get the voltage on C equivalent 2. So that is 9.50 volts across here. So if I take a meter and I measure that, that's what I get. I also have the charge on this capacitor along with its value. I can get the voltage on that. You will notice that these two voltages in series, they should add up to the source voltage, 20 volts. And if you take 10.5 and 9.5, they add up, those voltages add up to the 20 volts. And so that's just kind of checking my work. Okay, then next thing we need to do is undo this equivalent capacitance here, and that was this two in parallel. In parallel, they have the same voltage. Okay, now which ones are in parallel? This V1 was the voltage across that guy. V2 equivalent 2 is this voltage, 9.5. So I expect these two voltages to be the same, so they should be 9.5. Once I have C and V, it's easy to calculate Q. I could have done it here. I think I moved it over here. Yeah, I've got the voltage, the capacitance. I can get Q4. Then on C, okay, what haven't I done here? Okay, I need to get the final voltage on those guys. I got this voltage. Now I've got these two in series. The charge should be the same. I know what the charge is. It's got to be Q.
Go back to the last round.
Oh.
Go down. Your Q equivalent 1, 9.5.
Yeah, Q equivalent 1. Oh, yeah. Okay, so I get 9.5. And, okay, and that I do expect that to be the same as that. So that's a cross-checking with that. Then I can get the charge on this one, which I guess I did over here. So we've got the charge on this one, so we're almost there. We've already got the charge on this other one. We could did that way back here. Now we need to get I know the voltage on this one. Here's what I want. The voltage on C equivalent 1 is, since I got the capacitance C equivalent and the voltage, I can then get Q equivalent 1, 63.4 microcoulombs. You can see the confusion. I'm going to take that, and that should be the same on both of these. 63.4 is the charge on this one as well as the charge on this one. Then we can get the voltages. This one's going to be 3.17. This is going to be 6.34. Adding these two together, they should add up to 9.5. Okay, so you can see it's easy to get confused. He'll probably give you a little table you'll fill in. I encourage you to draw pictures. Again, you want to first go through the process of simplifying the circuit in one direction. Then you want to take these properties of whether they're series or parallel, whether you add the current, add the charges or add the voltages, going from this back here, and then we just work backwards as we go through this thing. I've got in blue here the things that I'm filling out as I go backwards in the circuit. Okay, kind of tricky. Yeah.
C2 and C4 are in parallel, so
C, what was C?
on the one to the left, the diagram to the left. C2 and C4.
Oh, are C2 and C4 parallel? Okay, we've got something in the way. Yeah, if this was strictly a wire there, then I could say they're in parallel. So yeah, you want to be careful that
That guy's here, so I can't make that one. However, this one I can. There's nothing between these two, so I can say that that in series is that. Is that? Yeah. Lots of ways of screwing these things up. Once you kind of get used to them, they're just kind of repetitive.
So
but
it matters the order you go in when you simplify.
yeah, and that's also why I'm suggesting draw every step. Don't try to cut too many corners because you are literally going to backtrack yourself. And so, yeah.
So C3 and C4 are in parallel or two?
Oh, these two?
Yeah.
These, he did that kind of trickily, but they're actually in series, not parallel. The catch of a series circuit is whatever goes into one will come out the other side and then go into the other one. So yeah, seeing these things, they're not always, the way they're drawn, they're not always really obvious. Like when I look at these two and say, oh, these are definitely in parallel. Sometimes, if this thing is stuck down here, it can look almost like the thing in series. It takes they can get kind of tricky. And you've got some homework problems where they draw some circuits that you kind of got to...
So that they're not all the same problem, the same piece? They're not all part of the same circuit?
Well, basically, yeah, this whole circuit, each of these are what we would say are equivalent circuits. Do the same thing. So we take these two, we make an equivalent capacitance. Then we say these are in parallel. We come up with another equivalent capacitance. And then these are in series. I come up with yet another equivalent
But
capacitance.
you have to take some values, right? So from 1 to 2, you take one of the... I think you took C3, right? Did you do that?
I'm not sure. I didn't
From
get...
1 to 2, you took C3 out to make a parallel.
Oh, right. I took, C3 and these two I just really combined into one, and that's why I gave it another name, C equivalent 1. Okay, and that does represent those two. Okay, so, okay. Okay, I'm starting to fry fast. Okay. If you have dielectrics, they can strengthen your capacitance. Actually, what they do is they weaken the electric field. The idea is if you stick some material in there, and it's made up of protons and electrons, and normally it's neutral, they're kind of randomly distributed. If they're stuck between the plates of a capacitor, they will start to get stretched and they can polarize. These minuses and pluses kind of cancel one another out in this region, but this side tends to become more positive on this side, and this side tends with these to become more negative, and so that there's what we call an induced electric field. E naught represents the electric field where that thing isn't present, just these two plates. When we stick the material in there, we deal with the electric field as kind of two parts. We're going to say E naught, the field of a vacuum where there's nothing in there, and then minus the electric field of E induced. The idea that if the electric field's this way, it lines these things up, so the induced charge is plus on this side, and on this side is minus, so the induced electric field goes back. It actually tends to cut into the main electric field, and so the actual net electric field, the combination of those two effects, is going to become smaller with the dielectric. Dielectrics are usually numbers 1 or greater, so the electric field, the actual electric field with the dielectric in there, is going to be the E naught divided by kappa. If we do voltages and we just integrate this is going to follow suit with that as well, as that the voltages across the plates are going to drop when K or kappa goes in there. That's going to make that smaller, and so you're going to have less voltage. When we play with the idea of capacitance, that is going to make the capacitance bigger because it's making the voltage smaller. When we deal with the capacitor, that smaller number in the denominator makes the overall larger.
So the big walkaways you want with this is the main one here is that for capacitors, that if you have the capacitance C naught with where it's just air filled or really vacuum filled, and then you put some material in there, it's going to become a larger capacitor. It can actually hold more with the dielectric in there. And so, again, kappa is usually 1 or greater, never less than 1. And then also the electric field gets weaker by a factor of kappa. So kind of these red boxes are the main thing you want to walk away with. And so we come to the last problem. I can make it. Okay, can you make it? Man. The inner conductor of a coaxial cable has a radius of 0.8 millimeters, and the outer conductor radius is 3 millimeters. The space between the conductors is filled with polyethylene, which has a dielectric constant of 2.3. So that's what we have been talking about. It also has another figure that's called the dielectric strength of this material, and that's 18 times 10 to the 6 volts per meter. Okay, now this dielectric strength, this is the ability to keep from breaking down. The idea, when we put a charge on the capacitor and it sets up an electric field, if we keep putting on charge, or let's say we keep trying to charge it up to a higher and higher voltage, at some point it's going to break down. Normally we'd say the charges on the capacitor do not jump the gap between the two plates, except during breakdown. And what you want to consider is that the dielectric strength, is how I'd put it in words, is the maximum electric field that the dielectric can withstand before breakdown occurs. Once breakdown occurs, there's going to be like a Van de Graaff generator arcing through the capacitor, and it's going to burn out. So this is a large voltage, and so usually for these dielectrics they can be strong, but we can, with high voltages, we can burn them out. Okay, so he gives us this value for that. Okay, now he wants to know what is the maximum potential difference that this cable can withstand, really, before breakdown. So the idea would be that I want to get the electric field inside here. Now, we're going to imagine I'm going to just keep putting more and more charge on this thing. So it's kind of a hypothetical thing I'm doing in my mind now. This would be E naught for the coaxial cable. We developed this earlier. This is lambda all over 2 pi epsilon naught r. This is that original electric field. With the material, though, it will hold this amount of, this will be the electric field inside. And the idea that this is going to become maximum whenever this lambda is at some maximum value. What I'd like to do is find that and then use that to go back and do the problem. Now we also will get the electric field. If you look down on this thing, the electric field is strongest where inside here? These lines are closer together. Is not the electric field stronger inside here and weaker as it goes to the edge? So this region here, right at R equal to A, would be right where breakdown might occur if it's going to start to get fried. So the idea is I want to find that Emax would occur, that value. I want to keep adding charge on here to build it up so that it gets to this value just where breakdown would occur. And I want to find what is that maximum amount of charge I have so that I can use that to answer the question. So Emax, he states in the problem, is this. So I'm making use of this equation. This is going to be lambda. This will be lambda max over here, 2 pi epsilon naught. The r is going to be the radius, and that radius, I'm using the radius a
because that's where it's going to be the strongest. So that's where I got the 0.8 millimeters coming in here. And then I solved for the lambda max. This is the maximum amount of charge I could put on this thing, this many coulombs per meter. I got a minus sign. I believe that should be plus to the 6th. You know, check my number. Oh, wait, maybe not. Maybe not. Anyway, this number's okay. Okay, and then once I have that, now I'm going to go back to get the electric field. Now, the electric field, I need to take the original electric field divided by kappa, the dielectric constant. And I'm using the electric field for lambda all over 2 pi epsilon naught r. And again, I'm adjusting for the fact that I'm on the inside here with this dielectric constant. And then I want to get the potential difference. He wants to know what is the potential difference between the plates. And that's going to be the integral of E dot dr as I go out here across, really think of me going across this thing and integrating. Going and sticking my values between R1 and R2, or the inside and outside, A and B. And I come up with, this is my voltage. And so the maximum potential difference we can have is this 19 times 10 to the third, or 19 kilovolts I could put across the plates of this thing, and it should still, well, that's right at the verge where it would break down or fry. So this would be something that could probably hold a large voltage if we wanted to employ that. So hope that makes some sense. As far as material, I know you're just brokenhearted, but good luck. I'll stick around if there's some more questions, but whoa, this is brutal, isn't it?